Did you know Sir Isaac Newton lived through a pandemic just like us in 1665? Well, during that pandemic, he actually invented a new kind of math called calculus. I think he was a little more productive than I was during a pandemic. Well, he created this kind of math because he needed a way to explain to his peers the physical science experiments that he was conducting. On today's adventure, we're going to explore Newton's law of motion. I wonder who that is. Come on in.
Hello, Payton. Hello, explorers. I heard you're going on a field trip today, so I just had to stop by before you left.
Explorers, you remember Amanda Wright, our education specialist? To what do we owe the pleasure?
Well, I have a question for our explorers today. Is air a fluid? And if you answered yes, you would be correct. A fluid is any substance that flows and has motion. So Payton, when you hear the word fluid, what do you think of? What image comes to your mind?
I think of water, like an ocean.
So we know the ocean is a fluid because it has water molecules. But did you know that air is only 1/1000th as dense as the water? So this means that our atmosphere is made up of something different than water molecules. It's made up of nitrogen, carbon dioxide, and oxygen, and other trace gases.
So what keeps us from being crushed by the weight of our own atmosphere?
Simply put, our body is filled with fluids that also exert pressure equal and opposite to that of the atmosphere. However, when we begin to travel up into the atmosphere, the amount of air decreases and so does air pressure. Do you know an instrument that measures air pressure?
I think it's called a barometer.
You're right. Air pressure and weather are important factors when we're thinking about lift and how much that contributes to the navigation of an airplane. And whether or not an impending storm may be too difficult to fly through. Let's say we take an empty soda can and set it on a table, and you blow on it from the right. What happens to the can? Newton's first law of motion is often referred to as the law of inertia. Why? When we look at an object at rest, like the soda can on the table, it will stay at rest until some force is applied. When a consistent force is applied to the object, it moves at a constant speed until another outside force stops the motion.
Thank you so much, Amanda, for helping us demonstrate Newton's law of motion. Now we better get going or we're gonna miss our, I don't want to spoil it just yet. Are you ready to go, explorers? Do you have your Explorer passport? If not, all you need to do is go to Center in the Square's on-demand page and download your free Explorer passport. And remember, all you need to be a good explorer is an imagination, a willingness to learn, and the ability to ask questions. Ready to go, explorers? And what better place to explore this than at an airport? Here we are at the Roanoke Blacksburg Regional Airport. Before we take a closer look at planes, we need to look at one more very important experiment. It is the Bernoulli experiment, and it is important to understand this in relation to how a plane flies.
Hi, my name's Jamila. I'm an explainer at the National Air and Space Museum's How Things Fly Gallery. And today I'm going to talk to you about lift. I'm standing in front of the Spirit of St. Louis airplane. It was flown in 1927 by Charles Lindbergh, and it was the first successful solo flight over the Atlantic Ocean. Now, how was this plane able to generate lift? How was it able to stay in the air? Now, I can explain that using this airfoil here. An airfoil is like a cutout or a cross-section of a wing. So if I were to take a wing and slice it into pieces like a loaf of bread, this would be one slice of the wing. Now, if we compare this airfoil to the Spirit of St. Louis, we'll notice they have very similar shapes. They have curved tops and flat bottoms. An airplane's wing will be shaped this way because of something called Bernoulli's principle. Daniel Bernoulli was a Swiss mathematician who studied the movement of fluids like air and water. And he realized that a faster moving fluid will have a lower pressure, while a slower moving fluid has a higher pressure. Now let's apply this to our airfoil or to a wing, so that when the plane starts flying and air hits the wing, you're going to get faster moving air on top. It's going to speed up because of the curve. At the bottom, where it's flat, you're going to have a slower moving air. It's not going to be as fast as the air on top. That slower air is high air pressure, and the faster air is low air pressure. That high air pressure pushes up on the airfoil or up on the wing, and that's why something as heavy as an airplane can fly. Don't believe me? Well, I have an experiment we all can try at home with a single sheet of paper. If I were to place this paper beneath my lips and blow, would it go up or would it go down? Let's see what happens. We notice that the paper goes up. And the reason why is because of Bernoulli's principle. When I blew my fast air on top of the sheet of paper, it was a lower pressure than all of the air in the room because the air in the room is slower than the air that I was blowing. So that high air pressure works from beneath and it pushes up on our sheet of paper. And the same thing is happening to an airplane's wing. And that's why something as heavy as an airplane, like the Spirit of St. Louis, is able to generate lift.
Let's take a look at the 4 forces of flight that affect an object's motion in the air. Lift is considered an upward force because as air passes over the wing, pressure decreases, creating an upward lift. There has to be movement. No motion, no lift. The thrusters of the plane help generate the movement we need in order to obtain lift. The thrusters push back against drag, which we will discuss in a moment. The next force we're going to talk about is how Earth's gravity affects the plane. All objects on Earth have mass and are pulled towards the center of the Earth with gravity. Without gravity, we would not have an atmosphere and life would not be able to exist. Gravity is a downward force that takes the mass of the object into account. We call this weight. Weight is mass times gravity. Weight works against airplane lift. I'm going to skip over Newton's second law for just a moment to talk about Newton's third law of motion. When an object is pushed in one direction, there is an equal and opposing force of the same magnitude resisting in the opposite direction. For an airplane's lift, the opposing force is the mass of the airplane and the gravity of Earth. Now let's talk about drag forces. When an object goes through a fluid, it creates a type of friction called drag, which is a backwards force. Have you ever noticed that a plane, except for the wings, is largely the shape of a cylindrical cone? This is to help reduce the amount of drag on the plane. The design not only helps the plane stay aloft, but also helps reduce the amount of fuel needed for takeoff, flight, and landing. Thrust is the result of the combustion of fluids in the airplane's engine as it works to overcome the drag force of the air. That is why thrust is in the opposite direction of drag. Thrust and lift forces work together to overcome the drag and gravity forces in order to be able to take off. All of these forces have direction and magnitude. Before we get into Newton's second law, let's talk about flight. Our sun heats the Earth's surface, but the Earth's surface is uneven. This uneven heating changes the temperature profile of the atmosphere. When temperature changes, so does air pressure. A packet of air will expand and move from areas of high pressure to areas of low pressure. We call this movement of air masses wind. Some winds are small, light breezes, and others are large, fast winds, such as the jet stream in the upper atmosphere. An airplane can take advantage of the extra push from the jet stream, or the pilot may need to navigate a different route to avoid flying against it. Because we have winds and air movement, planes are designed to navigate these air currents with smaller, additional moving parts on the wings. Let's begin with the ailerons on the front wings. When one aileron is raised and the other is lowered, the aileron that is raised controls the direction in which the plane can roll. This is helpful when navigating through turbulence and contributes to turning the plane. Next, we will look at the rudder at the back of the plane on the vertical wing. Rudders are used to yaw the plane in conjunction with the ailerons. Yaw means to turn. When the pilot presses the pedal to turn right, the rudder will move to the right aileron will be up, and the left aileron will point down. If you've been in an airplane, you may have felt this kind of turn after the airplane has left the runway and needs to be in the proper direction towards the destination, or when the plane has to circle the airport and wait for its turn to land. The last set of wings we need to look at are located near the rudder, called the elevators. As the name suggests, this movable part of the wing helps control the plane's pitch. The pitch directs the nose of the plane up or down. When the elevators are up, the nose points up. This feature helps the plane to climb or descend through the air. Now we have all the aerodynamic forces to talk about Newton's second law of motion, which states that objects will move further and faster when they are pushed harder. Since there is not some giant magic hand pushing the plane along, we have to rely on the plane's engine. The plane's engine is where the spark and combustion of fuel happens. Airplanes are heavy objects that not only contain the machinery that will make the plane work, but also carry people or cargo and jet fuel. Normally, the weight shifts from taxiing away at the airport, down the runway, and up until takeoff. But for this calculation, we won't go into that much depth. The purpose is to get an idea of how Newton's second law works. Mathematically, Newton's second law is represented by this equation, where F is the total force on the object, m is the mass of the object, and a is the acceleration of the object. We may not always know the acceleration of the object, so we can substitute velocity divided by time as the acceleration. Would you like to find out how much force it takes for a 747 jumbo jet to take off? Get your passport and pencil and write these numbers down. The average 747 weighs 334,400 kilograms. The speed of the plane is fueled by the thrusters under the wings. The average takeoff speed of a 747 is about 200 miles per hour, or 89.4 meters per second. We will use 89.4 meters per second as our velocity. I also found that it takes an average of 27 seconds for the airplane to take off. This will be our time, t. Now we substitute our numbers for variables to give us F equals 334,400 kilograms times 89.4 miles per second divided by 27 seconds. This gives us a force of 1,106,864 newtons. Remember, we did not take into account the angle during takeoff, and the extra help from the lift force reduces that calculation, but not by much. We also did not need to think in too much depth about the drag force and gravity since we looked up our numbers and can safely assume that these forces have been taken into account. We wanted to show you a simple calculation to help you think about Newton's laws and force. There are a lot of great resources out there that you can look up that go into further detail and include how to calculate angles and drag forces for more complex problems about aerodynamics. Welcome back, explorers! Did you have a good time at the Roanoke Blacksburg Regional Airport? I'm just glad I didn't have to force you to come with me. Remember to download your virtual passport at Center in the Square's on-demand page, and always keep exploring. Have a good day, explorers!